problem solving and formalized reasoning. As you move forward in physics, you will encounter word problems. It's just how they assess material. So having productive strategies and becoming sharper in your problem solving skills is going to be part of the main goals and learning objectives. So let's talk about formalized reasoning. Solving problems with formalized reasoning, what your main task is going to be is translating a word problem into some algebra and math in order to solve for a quantity. So you're giving word representations, and you need to move that over to the numerical realm, the symbolic and numerical realm. So there's this translation that goes on, and it involves representation. It involves reading comprehension. This is an involved process. You're hearing this, right? These terms that come up, reasoning and concept application. We're going to have these concepts in physics that we need to apply in certain situations and correctly. How do I know which concept to apply? Doing the algebra and math, once I get it set up with all of that, doing the algebra and math, and then when I get done, reflecting on the process and the answer. There's a lot that goes into this process, and so I wanted to lay down some tips and strategies for moving forward into solving problems in a more formalized way. And so what I mean by formalized is systematic logical application. And this is going to be with clear justification of reasoning. Formalized often means that we're very explicit in the logic that we carry through in solving a problem, and we provide evidence and justification between steps. Very formalized and has symbolic representation. Okay. Representations are how ideas are communicated. Common types of representations, we're going to see a lot of them, and I wanted you to be prepared for how many you're going to see, the types and what their uses are. Of course, we're going to have words, vocabulary, and terminology and definitions, all of that formal sort of, this is how to represent the ideas. Related to that are the concepts, the symbols and equations that come out of the definitions, concepts, and their mathematical interpretations, right? Symbols and equations, we need to represent ideas with symbols. They're going to get translated to me, a sentence of math, an equation. We can use graphs, tables, diagrams, or just general sketches to aid us in our problem solving. And the most adept problem solvers use all of those in order to solve problems. And of course, we're going to have numbers, like we're going to solve for a number typically. And so it's not just, right, this sort of, I'm going to do some algebra and numbers. There's much more going on in there. And the nuances of how do I coordinate these different representations into scaffolding my problem solving will become a skill that you practice and practice. And so we are going to use representations meaningfully in complex problem solving. Basic symbolic representation has some common strategies that are convention and also can be used mindfully, right, to communicate well. That's what you're doing, is you're communicating different symbols or concepts. So meaningful symbolization includes choosing something that makes sense in the context of the problem. For instance, if we're dealing with distances, often D is used for D for distance. Also, position is often referred to in the x coordinates. So x can be used for a symbol for distance or position. All right. So in the context of the problem, there comes out that it may be velocity, so you use V, or force, so you use F, mass and acceleration, M and A. There's these, makes sense to use certain letters in certain situations. Often you have an initial and final, so you'll have an I and F, a V initial velocity, a VF, a final velocity. And so the trick here is to choose something that another human being, maybe one not even as smart as you, could figure out, right? And also if a variable is defined in the concept or if it's defined in the problem already, do not adapt a new symbol. Maintain the original symbol that was defined for you, and that is convention, adapted practice in the maths and sciences. All right. Something I see often is that students will change the case of symbols. For instance, I put on there T. Little t is not the same as capital T. For me, little t is time and big T is temperature. Those are very different concepts, right? And so don't just go about haphazardly using a capital as opposed to a lowercase. They have very specific definitions. If you look at the subscripts, I was talking about that before with the initial and final. You may have intermediate ones. You may have two different objects, object A and object B, object 1 and object 2. And so we reserve subscripts in order to add additional meaning to original symbols. Superscripts are for exponential applications. So if you see a v squared, r cubed, that sort of thing, that has the power up to r cubed, right? V squared, as opposed to v initial or v final. The initial and final are both subscripts, and the exponents, general exponential operations, are the superscripts. Also, I wanted to bring up Greek letters. In science, we use Greek letters. It's sort of a tradition handed down. And the symbols used for typically for physical constants or special functions. You will see Greek letters. So don't freak out. If you see a Greek letter, you'll get used to Greek letters and recognize them. Those that look like Latin letters are rarely used. So for instance, a lowercase letter alpha looks like a fish to me. That's how I think about it. It looks like a fish. So that's the lowercase. The uppercase is given by what looks like an A. And so you will see that the lowercase version of alpha is used, but not the uppercase because it's already an A, right? It's confused with A. You can see this with other ones. Let's see, there's a row you use. Of course, there's pi. There's very frequent, epsilon is out there. There's very common Greek letters that you will come to recognize and we will continue to use. There's different types of symbols and numbers. Just to remind you in problem solving, in equations, there's variables and constants. A variable is a quantity that may change value, as opposed to a constant is a quantity that does not change value. So I had a couple of examples up here. This equation on the left, this formula here, deals with rho. This is Greek letter rho, which means the density equals mass over volume. And so when I think about the symbols in here, the density of an object does not change. So notice that we're using a Greek letter for a constant value. We may have to solve for this value in a problem, but the property of the material is a constant feature of that material, as opposed to if I look at mass or volume, I can have a different size of that material that I'm looking at that has a density, and those are variables. Those can change value. And so we think about what can change value as opposed to our constant values. Over here is an equation for potential energy. When we think about potential energy, we're thinking about changing height for gravitational potential energy. G is a constant. That's the 9.81 meters per second squared, the value of gravity. This is a constant value, as opposed to the mass or the height can change value. Those are variables. Okay, so when I look at formulas and equations, I keep in mind like what type of value does that symbol represent, a variable or a constant value. Also, when we're working with problems and problem solving, of course, we're going to be given knowns and unknowns. Some things we're going to have to know in order to solve for the unknown, which is the point of the whole problem, right? So the knowns are variables that are given as given numerical values in the problem statement, and unknowns are the ones we don't know. And so you will become more skilled at identifying knowns and unknowns. as we move forward. And it's good to identify them, assign a symbol to them, and write out what they mean, right? So up here I might write out G equals 9.81 meters per second squared. I know it, right? It's a known constant. I may know other variables. They may tell me that the height equals 60 meters. I may know that. So write the knowns out, and then you may have to solve for, what is the mass? I don't know what the mass is, but it's a symbol that's a variable in the problem. And so I write all that stuff out. Expressions of relations, just to remind you of some terminology, mathematical terminology. An algebraic expression is just some constants and variables combined using standard mathematical operations, right? So I could have 1/2 mv squared plus mgh. That is an algebraic expression, okay? There's no equal sign in it. It's just some symbols, and there's an addition and multiplication, exponents, etc. An equation has an equal sign in it. That's what distinguishes an algebraic expression between and an equation. Is it now if I put equal sign here, let's say I did this, now I have an equation. I have one thing equal to another. It's a mathematical statement indicating two expressions are equal to one another. Okay. A formula is an equation expressing a relationship between a constant and variable quantity. So when I think about rho equals m over v, that's a formula. There's a constant and variable quantities. Yeah. F equals ma. All right. I could calculate the force if I knew mass and acceleration. These are formulas. They're equations, but more specifically, they relate concepts, ideas to one another. That's a formula. And I wanted to make a note here. Very frequently, you will be required to use formulas to set up your own equations. Very frequently. This will be one of the tasks that is the hardest thing for problem solving to adapt to, is getting your own equations. And what I have to say about that, let me say a little bit more about that. So problem solving, and the big deal here is to assess that you can identify relevant concepts and apply them in novel contexts. That's how we know that you know physics, for example, is that you can identify the relevant concepts for a problem and that you apply them accurately in that situation, and it's a novel situation. It's not one you've seen before and kind of, practiced, but can you see a new situation where that concept applies? And can you apply it consistently in that new novel situation? So most problems you will be given will not be plug and chug, but we all want this. Just look at the equation, pick out an equation on the equation sheet, and then you can plug things in and get the answer, and that's plug and chug. But it's not going to be that way. I'm sorry to, some may be like that. Some may be like that, but most won't. Concepts will provide a general form of an equation that must be adapted to each different problem's context. And you will best serve yourself by developing a recognition of this, is that it's not just look at an equation, pick one out, but develop one based on each individual problem. So you're going to develop equations on your own and reason for yourself. Also, you will be required to show all your work in order to earn full credit with me. So it's not just the answer, you must express your reasoning. So what does express reasoning mean? Expressing reasoning is justification that does not include the algebra. It's not just the algebra and the answer, all right? For me, identifying a concept. Can you write down this is Newton's second law, or this is conservation of momentum? Can you identify the concept that is the bigger idea that applies in the problem that suggests the sort of formulas that you're going to use? Any words or phrases or sentences provided to justify using these? For instance, at the top of projectile motion, you see at the top, that means the velocity in the y direction is 0, and if it's reached its vertex of its motion. So those words mean things, right? We can recognize anything coming out, phrases in the problem statement that justify using concepts and techniques. Why did I plug in 0 there? Well, the words told me something. Any representations that support setting up and solving. We will be using diagrams and sketches and graphs, right? And so when you set that stuff up, it's not just that show me that you know how to do it, but when you use those, it scaffolds your reasoning. It helps you think about the problem. And I want to see that it will help you learn to use those effectively to solve problems, and they will be required as your work in justifying your answer to this problem. When you're doing this, we're going to be mindful of notation, presentations and syntax, orders of operation. Explain your decisions you made for solving problems. And also reflect on the answer process you used. I'm a little bit more follow-up, sort of let's think about what we did and why our answer makes sense. And I will require you to show some of this work on your assessments as well. Aspects of problem solving. There's a lot of aspects of problem solving. I was looking at this earlier, and there's a lot of aspects of problem solving, and I can understand why it's intimidating for some people. And so it's my intention to help provide the scaffolding you need in order to make problem solving productive for you consistently, right? Often with problem solving, we get stuck, and knowing why we get stuck and where we get stuck and what to do when we get stuck is great things to know how to do, right? If you're a coder, it's not that you can code, it's that you can debug well and find your missing, whatever you miss in your code, right? So aspects of problem solving, where can we refine and make sure we're paying attention to do things well? The first step here is interpretation and reading comprehension. If you're not reading the problem well, if you're not paying attention to detail, and noticing what words are in there, because words mean things. I don't know how you use words outside of our interaction here, but for me, I will stand with the assumption that words mean things. And reading comprehension of the problem statement. I often see students who don't read the problems well, the setup of the problems well, and then get completely off track with solving the problem because they didn't set up the problem well. They didn't clarify initial situations or assumptions, and so there's a level of reading comprehension that's critical with problem solving. So I just mentioned that. Evaluate your assumptions about the problem setup and statement. Okay, where's the initial and final positions? I'm trying to think of examples, but we'll pay attention to the details in the problem statements as we move forward. All variables in a problem statement, whether known or unknown, we're going to assign a meaningful symbol, and I call this defining the variables, and this will be required work that I will check for. Draw a sketch, graph, or diagram as a tool to aid in encoding the problem details. So as you read the problem and dissect it, we can draw graphs, we can draw pictures, we can set up equations, we can define our symbols and encode the problem details, get an idea of what's going on, right? What is it that we know and don't know? What's the picture? And get this feel of the physical situation. And we can start applying concepts in there and setting up equations. Any sketch or diagram, and I will show you typical ones that help for some problem-solving situations. And there will be some that you will be required to know how to use, such as a free body diagram. You will be designating a coordinate system as appropriate. This may not be something that you're used to doing prior to entering into a physics class, but you will start using that prerogative in your lifetime, is assigning your own coordinate system, especially with working with vector quantities. For instance, if we have initial velocity up and acceleration down, we need a coordinate system in order to take into account that there's a negative sign in there somehow. So which direction is negative? Okay. Recognize algebraic techniques, isolate variables. We may recognize that it's a quadratic equation, or we need to solve linearly, or etc. Right? Don't derive a formula for unknown variable algebraically. This will be challenging for some people because until you get used to symbolic representation, your mind prefers to see numbers. Numbers have anchored meaning in our brains. As you evolve with symbolic representation, all right, let me give an example. Let's say I want to say the final velocity equals the initial velocity plus acceleration times time. Let's say I want to solve for time. So I'd solve this equation for the t variable. For me, this is a pretty easy thing to do. Even though there's a lot of letters in here, I think of each of these as a concept and I move them around. For other people, it may be easier to see something like this and say, I need to solve this equation for the time. It may be easier to say, oh, this is the thing that I'm solving for. Everything else is a known value, and I isolate the t on one side and everything else on the other, as opposed to the one above where there's a symbolic equation. And that's why I was talking about derive the formula for the unknown variable algebraically, then plug in known variables. So I would prefer for you to solve for t in this situation, then plug in 9, 7, and 2 into that form to solve. Okay, we will practice this as we move forward, and you'll see this in a couple of examples I have coming up. Be sure when you're doing your math and deriving and algebra, etc., attend to your detail, especially with orders of operation I see issues with often with students, and also using a calculator, like when you're plugging things in. If you have a larger face graphing calculator, that's a lot better, that you can see like all of the things that you're entering into your command line. If you have a smaller face one, that's fine, but I do recommend something that you can see what you're entering on the face there. We will be using graphing calculators, so if you have a graphing calculator, one of these, that's fine. We will be using Desmos as well. So those are, you will be responsible for knowing how to graph. So when you're using your calculator, pay attention to detail there. And so those will be skills that will grow for you as well. Finally, problem solving, like I said, reflection. Does the answer make sense? Look at the number. Is it in the right scale that you expect it to be? For instance, if you're flying an airplane, there's a certain scale of numbers that speeds for airplanes are appropriate, right? Or if I was looking at the mass of a piece of ice, depending on how big it is, right? We can guess if we're thinking about space, distances in space. Is it the right sort of scale for distance in space? So numbers, they're units. We're going to learn how to look at units and did you arrive at the right units using dimensional analysis? Expected range of numbers or answers. So like maybe the coefficient of friction is between 0 and 1, and did we get an answer in there? Estimates, limiting behaviors. If the radius goes to 0, what do we expect the function to do? So there's limiting behaviors we can look at as well. These will also be skills that will come along for you as you move forward in problem solving when you reflect on the answer. Another thing I'm going to emphasize is metacognition, or this deliberate awareness of the processes going on in your mind while you're learning and problem solving, right? What is it, like if we're sharpening, what we're really doing is we're building neural networks, right? Neurons communicate with one another, and the system gets going and clumped together, and then they start firing together, and the more it fires together, the stronger the network will be. And so the mindful management of that as you're problem solving, can you get a system to fire reliably, consistently, right? Deliberate awareness of the processes going on in your mind. How can you establish this repetition, this productive problem solving and productive learning process to have strong, meaningful learning? Okay, and there's things that we can do in problem solving to help sharpen our problem solving skills. For instance, asking yourself, what are the relevant concepts, right? Every time you approach a problem, it's not just that you dive into solving it somehow, but you're thinking about what are the concepts that apply here. You're still staying kind of mindfully, it's like a meditation for me, but you're mindfully aware of moving through that problem solving process. How do I know the concept applies here? What are the features? Making sure you're noting features of the problem. Do you have a clear overall strategy, or are you going to kind of move forward one step at a time while you figure things out, which is perfectly fine. It's a perfectly fine way to solve problems. That's how human beings have solved problems for thousands of years on the planet, right? Is just moving ahead and ahead and ahead. But at some point, it may be that you see the bigger picture of the problem solving process for a problem. And can you identify it? Can you recognize? And that's a pretty good place you want to get to, like for an exam, especially for the final exam, is moving there. Can you recognize the problem? Okay. In which part of the problem solving strategy am I? Are you in the concept application? Are you drawing a picture? Are you setting up your equations? Are you solving? Are you plugging in the calculator? Are you reflecting? Where are you in that, right? And knowing where you are can also be helpful when you reach out for support. If you get stuck someplace, you know where you're stuck. And when you go see a tutor or you go see your faculty, you can be more specific about the help you need instead of saying, I don't know where to start, right? You can say, well, I got this far. I understand this much. And I know maybe I need to go here, but it's not clear, right? So you have this larger awareness of the problem solving process that you're engaged in. So when you get to the end, maybe, and you got the right answer, you're like, what did I do that worked? Review over it's not just, oh, I got the answer, I'm done, right? But go back, we're building strong neural networks. Go back over and review it. Reconnect those neurons so that you can get this, a good connection for making sense and consistently solving problems correctly. How does my answer make sense in the grand scheme of things? So that was the strategies I talked about just a second ago with checking your units, and is it the right scale, and is it the thing that I was kind of looking for? Did I expect a value in some way? Finally, how does this problem differ from other problems of the same concept? So I was mentioning earlier that we're going to be doing novel problems. So this problem will be different than this problem will be different than this problem, but the same concept will apply for all of them. And how are they the same and how are they different? I found this to be a very productive question to ask people as we move through examples. And I will choose examples that highlight different features of the problem, and they will be different in different ways so that you can see the concept applied in different ways and different subtleties of the concepts. Okay, so different problems will emphasize those different things. How do the problems differ will be a productive question for you to ask. What was given here and what was the unknown? How was this problem oriented? The angles may have been different, or the different masses, or what have you, right? How were they different? What was the different emphasis of the concept? So it could be, were you finding a net force as opposed were you finding the net acceleration? There's different emphases you can put in a problem. So when you're looking at all that, when you're bringing your problem solving and this conscious problem solving together, you're going to get more productive learning. It's not just getting the answer and being done. It's that you're making your time a little bit more working for you. So what you're going to do is practice and establish habits, right? We're establishing a neural network, a stable neural network, so we're going to deliberately practice technique and establish habits of mind. And I'm going to do this with simpler problems. It may feel a little, I hope not condescending, but we're going to do some simpler problems just to illustrate what I'm asking to be done. And as we establish this, these habits of mind and techniques, as we move forward to harder problems, you're going to have them established because the problems will get harder. And if you structure your problem solving well, as we move to harder problems, you're already going to have that in place and have that to move forward with the harder problem solving. So we're going to apply these in practice. The first problem I have for you is about giving gifts. Devin has a spool of ribbon, L feet long, one spool. Devin uses G feet of ribbon for each gift basket she wraps. What a nice person. How many gift baskets, N, can Devin wrap from one spool of ribbon? Okay, so we're not given any numbers here. No numbers. And this may look like the problem from hell for some people, but let's work with it. Okay, so this is broken up into parts. Let's just do the first part here. Locate each symbol in the problem and write out what it represents. Okay, so I'm going to say here there's three symbols, L, G, and N. Yes, L. One spool is L feet, so I'm going to locate each symbol. So I have L, and write out what it represents. So, and when it says write out, that means like write words. I don't have numbers here, and that's not what it's referring to. It says write out what it represents, not what it equals, right? What it represents. So L is the, I'm going to say total length of ribbon. I don't think anybody's going to fight with me on that. L, one spool of ribbon. The whole spool equals the total length of ribbon. All right. So Devin's using this ribbon to, she's going to cut the ribbon up and use so much ribbon per gift, right? So they're saying G feet of ribbon for each gift. So G is going to be the length of ribbon for one gift. And N is in here. N is the number of gifts. So when I say define your symbols, this is what I am referring to. Define your symbols. I don't need to know what values they are. All I'm identifying is the symbol I'm using to represent it in equations, and also the words that go with describing what that thing represents. Okay, so A is done. B, develop an equation relating these three symbols. Draw a sketch as needed. I don't think we need a sketch necessarily here, right? I kind of said it. We have a long length of ribbon, and then we're going to divide it up into even pieces of ribbon for each individual gift. Each individual gift gets a certain amount, right? So that could be the picture, but I'm not going to worry too much about a sketch. It's pretty simple equation, because when I think about it, the total length of ribbon is going to be the length of ribbon per gift times the number of gifts, right? The length of ribbon per gift times the total number of gifts has to equal the total ribbon, right? Cut it up into pieces, boop, 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 right? N number of pieces, and they're G each. It has to equal the total length, L. And so that might be a picture that you could draw in order to get, like, encode your information a little bit better. We're not given any numbers. I just arbitrarily picked 4, right? Like, we don't know. So that's done. Solve the equation for the number of gift baskets as a function of the other two variables. So it says solve for the number of gift baskets as a function. What the heck? Okay, so let's dissect this. Solve the equation, solve for the number of gift baskets. So we want N on one side. So for me, it's asking solve for the number of gift baskets as a function of the other two variables. So we're going to put the other two variables on the other side. So let's go ahead and do some algebra on this. I want to get N by itself, so I'll divide by G on both sides. And when I do the algebra here, I get N equals L over G, which we might expect, right? We have a total length. We divide by the length per gift, and that would give us the number of gifts. So this is what they're asking for in this problem. Solve the equation for the number of gift baskets as a function of the other two variables. So we've done a problem. We don't have any numbers, so we can't really solve it. But when we look back at, and like I just explained, when we look back at the problem-solving process, I can say, oh, well, this equation makes sense. The total length, divide by the length per gift, will equal the number of gifts. Like this equation is making sense to me on some level, right? And as we went through, we were really deliberate about setting everything up, defining symbols, making sure we're thorough, and paying attention to detail. Okay, really easy problem, but there's this formalization that goes on, right? We're taking out this sort of slick, really quick mind tricks, and we're making each step deliberate. Okay, and as we move forward to harder problems, this is going to serve us well. The next problem I have is a little bit, I have numbers in here on this one. Favor bags. Maria buys a jumbo container of candy to be evenly divided up to make favor bags for her son's party. A total of 12 children will be at the party. She's nice. Okay, identify and label each variable in the problem. Okay, we're not given any symbols here. On the previous problem, we were given symbols, but on this one, none. So we need to identify what is going on here. Okay, Maria buys a jumbo container of candy that will be evenly divided up. Okay, so for me, there's like this total number of candy. All right, let's say C, and it says identify and label each variable in the problem. So let me do this down here. The total number of candy, let's say capital C subtotal equals the total amount of candy. And it's to be evenly divided up to make favor bags for her son's party. So we're going to have candies and favor bags. It says a total of 12 children will be at the party. So it seems like the number of favors bags will be 12, right? The number of favor bags. So the number of favor bags is going to be 12. And so the total amount of candy will be divided up evenly to those number of favor bags. So it seems like that we need another variable. That's the number of candies per bag. Okay, I haven't put symbols in here yet. I'm just saying, okay, when I read the problem, these are the constructs that are coming out, these variables. What are the quantities, right? We do know the number of favor bags, 12. So let's assign symbols here. I call this little c is the number of candies per bag, and I'll call this n, number of favor bags. It's arbitrary what you call those. You may have thought of other variables in there. Doesn't matter. As long as you're doing this step, identify and label each variable. I would accept if you put C and F maybe here, or B, number of bags is B. That makes sense. Maybe number of bags is B. As long as you've defined them, you've written that information out for the person reading your problem. And if it makes sense to you and you communicate it well to another person, this is your step to communicate it well to another person. Okay. Develop a general symbolic equation for the number of candies. So just like we did in the previous problem, we're going to take these symbols and develop a symbolic formula to relate them all together, right? Draw a sketch as needed. Do we need a sketch? I mean, we have a big container of candies, and there's a bunch of candies in there, and then we're going to divide them up into 12, right? So the total number of candies, C total, will equal the number of favor bags times the number of candies per bag. We're getting there, right? Develop a general symbolic equation. We did it. That's it. Okay, so hopefully this is feeling a little bit natural, like it makes sense to identify these quantities, and then when we put them together into equation, the concept that each symbol represents relates well to the sentence, the concept that that whole formula is saying, right? The total number of candies has to equal the number of candies per bag times the number of bags. Makes sense. Okay. Determine how many candies in each flavor bag if the jumbo container holds 84 candies. So we're going to write this. Let's see, C total equals 84. We know that N equals 12. It says determine how many candies. So I want to solve for C. I'm going to take this equation and solve for C. Little c. Not big C total, but little c, right? So if I want to solve for a little c, I would divide each side, and I will get quicker about doing algebra as I move forward with the curriculum. So solve for c. We're going to divide by n on each side, so we're going to get the number of candy equals the total number of candies divided by the number of bags, which you may have already thought about this. We're going to take 84 and divide by 12. If you're good at math or recognize that right away, you could plug it in your calculator, but this is 7 candies per bag. And that is the answer. I would put a box around this here. I would also put a box around this here. Right? And see how developing this formula is different than using it to solve for a value, whatever variable we're given. And this is why I was mentioning before, is that I will be solving for the formula for the symbol of the thing I'm solving for prior to plugging numbers in. You see that step? This is the step that I want to see in there that you're able to do. Some people may have put 84 and 12 into this step up here. Not necessarily wrong, but what I'm encouraging you to do is work with symbols as long as possible and develop your symbolic manipulation and reasoning to more depth. And this is, to me, a signifier that you think in terms of symbols. They're just numbers. You'll become less enamored with numbers. Numbers are cool, but they're not as cool as symbols, okay? Concentric circles. 2 concentric circles have circumferences 30 pi feet and 40 pi feet. Find the area of the ring-shaped region between them. Okay, so they're on top of each other, right? Concentric. Con, same, center, same center, concentric circles. So I'm going to draw these 2 circles over here, and I apologize for my lack of art skills. So I have a smaller and bigger circle, and of course they're going to be concentric. Here they are, they're concentric. And what we're trying to find, and notice that I'm drawing a general sketch here. I'm just drawing this general sketch. The area we're trying to find in here. And so this is helping me encode the problem. Right? When I talk about metacognition and what I'm doing and being aware of it, you see that here it didn't even suggest to me use a sketch if needed, right? I went ahead and I started doing it so that I can see what's going on and start encoding the information and defining symbols as well, right? Because when I draw circles, we know the defining dimension of a circle is its radius. So these 2 things have a radius. I'll call it radius 1 and radius 2. Also, both of these circles will have an area 1 and an area 2. Why am I bringing up area? Well, they brought up area, really. Find the area of the ring-shaped region between them. Okay, so this is some geometry from a while ago. We're given circumferences and we're given area. Let's recall the circumference of a circle is 2 pi times r. The area of a circle A is pi r squared. Okay, so we see that there's a radius in both of these equations, these formulas that relate our ideas together, right? And I have 2 different ones. Notice that I use subscripts. I have a smaller one. I'm referring it to as 1, and the second one, the larger one, is 2. And I've used subscripts in order to do that. I've drawn them separately to begin with because they gave me information, right? They tell me that C1 equals 30 pi and C2 equals 40 pi. And so I'm encoding this information. I'm writing out what I know and what I don't know. I have a general form for C, and when I use it to solve for each individual circle, I can use the subscript 1 and 2 in order to delineate the two of them. So I have to relate these circumferences to the circles to get at the area between the two, the ring here. Okay. So it seems like we need to solve for the radius. And I'm going to say this loud so that we have a problem-solving strategy as we move forward, right? I can kind of see a few steps ahead. I can solve for radius. I'm given circumference. I can plug it in and I can solve for radius. Well, once I get the radius of the two, then I can find the area of the two because the area has the radius in it. So once I find the radius, I'd put it in here and I'd be able to determine what A1 and A2 are. But that's not the end of the problem because that's not what they're asking for, is two separate areas. What do I do with those two separate areas? Well, to find this region, all right, basically what you're doing is you're taking the area of the larger one, A2, and you're hollowing out, you're taking out of the center the area of the smaller one. So the total area, which I can just say, or let's call it a ring, right? That makes sense. They're calling it a ring. Find the area of the ring-shaped region. So I'll call it a ring, will equal A2 minus A1. Okay. So I'm like working in symbols. I'm going to notice that if I say a ring equals A2 minus A1, well, that will be, and we can make a note here, A1 is pi R1 squared and A2 is pi R2 squared. So when I take A2 minus A1, I'm going to get pi R2 squared minus pi R1 squared. I'm just going to factor pi out here just to make it a little bit easier. R1 squared. Okay, see how I factored that pi out? It's not necessary to do that step, but it is the elegance that we practice in math and physics. So let's see, if I get R2 and R1, I can, if you wanted to, you could say, yes, I know, yes, yeah, I heard you, yeah. I got a question. Can we factor this one more time? Yes, you can factor it one more time. Remember that the difference of squares here factors into this R1. Okay. You could do that if you wanted. It's arbitrary to me. Okay. So that's our bigger plan. We're going to find these radii. Once we get the radii, we can plug it in here, and we do this step, and we're going to have the area of the ring. Okay. So I'm going to say for C1, 30 pi, I know that has to equal 2 pi times R1. That has to be a true statement. Here's the general form of that formula, and I apply it in the specific situation with C1, and I have to do it with C2 as well. When I solve these two equations, and if you need to, you can pause for a moment. I'm going to go ahead. I divide by 2 pi on both of these equations, right? Divide by 2 pi here and 2 pi on this side of this equation. So 30 pi R1 equals 30 pi divided by 2 pi, which is 15. Nice. I'll do the same thing for R2. It's the same sort of equation, same structure, same knowns and unknowns, and so I get this to be 20. And of course we're in feet, so I'm just going to note feet here. These are nice intermediate answers that I might check for example, on a quiz or an exam. Did you get any immediate answers that I can give you credit for? Okay. So now that I have 15 and 20, I can use that down here, right? R2 equals 20 and R1 equals 15. So I can plug those values in. I'll get pi times 20 squared minus 15 squared. plug this into the calculator. 20 squared minus 15 squared is 175 pi. And just to have a decimal, a ring equals, I'm going to multiply that times pi. Let's see, 549.78 feet squared, right? We have 20 feet squared and 15 feet squared, which results in feet squared. So I'm going to round this. Notice that I have 1 sig fig. I'm going to round this to 2, 550 feet squared, and let that be the end of the answer. Okay. Does that make sense? Yeah, I have 20 and 15 feet. That's somewhere in the hundreds of feet. I'm okay with an area being that big with that big of circles. All right. What else can we look at here? And like I noticed, the units get squared in here, so I get feet squared, which is what I expect for the dimensions of an area is square length squared. Okay. I didn't use this version of it. It was just as easy to do this. So we're formalizing our problem solving. Notice in this situation, it was prudent for me to kind of map out the problem strategy and go there. Sometimes you won't be able to do that. Sometimes you just get to, oh, I found the radii, and then kind of leave, like, how do I find the area of the ring a little bit later in the problem solving process instead of thinking of it beforehand, which is fine. It may be something that works productively. But at some point, it may be that you keep trying to map out, like a chess, like if you play chess, right? You keep trying to map out farther and farther in the problem, like how far can I think out the solution for this before implementing the solution and the solution process. What do I expect the end of that process to be? Sometimes you can do it in the beginning. I don't expect you to be able to do it a lot in the beginning while we're working on this, but as that may be one of your goals to do.